Okay, let's get started. Welcome back. Hope you are enjoying homework 2. Okay, so today, very exciting lecture, this one and the next one, at least for me. We'll talk about two things. We'll continue the discussion from last time, put it into a more practical direction, talk about achieving the entropy rate for Markov processes, stationary processes, and so on. And we'll dive into like compressing text data. And then towards the end of today's lecture, depending on how much time is left, I will start with LZ77, which is really the most common compression technique you will encounter. And we will continue with that in the next lecture. Okay. So quick recap, right? We talked about a lot of things. So this is just a summary of what you will need really today. We talked about Markov chains. So if you remember Markov chains or Markov processes, for a given k, a kth order Markov process means that you need the previous k symbols to predict the next symbol, but no more. So looking at like further past doesn't help you. In particular, a first order Markov process is the current step depends on the past step, but given the past step, it doesn't depend on anything before that. Stationary processes are like a generalization. They are any process which is time stationary, time invariant, which means that the statistics don't change with time. We mostly will talk about stationary processes only in the context of like certain theoretical results, but in practice, I guess, just think of a process. Given the past, you can predict something about the future. So that's the process in a way. We talked about conditional entropy, which answers the question: given you have two random variables u and v, and given v, how much uncertainty is left in u, right? On average. And then we talked about this specific one, u given v equal to v, which is given you know that your random variable v is equal to v, how much uncertainty is left in u. Or you can talk in terms of bits used, right? So this one says like if I know v, how many bits do I need to compress u? And this one says if I know v equal to v, then how many bits do I need to compress u? And we looked at a few properties. We looked at the chain rule, right? If you remember, where we had like the joint entropy of u and v is simply the entropy of v plus the entropy of u given v, right? We looked at the inequality that conditioning reduces entropy. So just some results we saw, which you will use in your homework. And then we talked about the limit. So you have a stationary process, and what you can do is you take your n plus 1th symbol, you condition it on its entire past, and then you keep increasing n. So in the limit, what will happen is you are trying to capture, given I know the entire past, is there still some uncertainty left in the next symbol? Is each new symbol adding some entropy, some randomness, some bits? And the limit is called the entropy rate. Another equivalent way of expressing it is you think in terms of like a block. So you take, say, if I take the first n symbols and I take the average entropy, and then you keep increasing n, and then again you take the limit. So and obviously like if you have done limits, you will know that like this will be at the end of the day dominated by the large terms, right? Like the first few terms don't matter. So it's like not very hard to prove that these two are equal. You just need to use stationarity and some properties about limits that you might have seen in calculus. But you don't need that for this class. Okay, so with that in mind, let's quickly do the homework, which will sort of refresh our concepts about conditional entropy, entropy rate, and so on. And then we'll move on. Okay, so we are given a Markov chain in this question. We don't say that it is a stationary Markov chain for now. So how is it described? We say U1 is Bernoulli half. Okay. And let me draw it in this diagram sort of way, which is easier, I think, to understand. So if U1 is 0, we say that U2 has to be 1. Yeah, right? Is that clear? Basically, we are saying that if U1 is 0, then there is no chance that U2 is also 0 because this term is 0. And if U1 is 1, then the next symbol is either 1 or 0 with equal probability. So like this sort of thing. This is 0.5. This is 0.5. So the first question we ask is, what is H of U1? Anyone wants to guess? The entropy of U1. This doesn't even need the class from, like I told you, U1 is Bernoulli half, right? So the entropy of U1 is just 1 bit because it's a Bernoulli half random variable, right? So that's good. Okay. Now I ask you, what is entropy of U2? There was a question on ED I saw where like U2 is dependent on U1. So what do you mean by entropy of U2, right? So at the end of the day, all of these are random variables, whether or not they depend on anybody else, right? So any random variable, you can compute its marginal distribution, you can compute its entropy, right? Just follow the formulas. So what is, for example, what is PU2 equal to 0, right? So we did this last time, so I won't spend too much time unless anybody has questions. So you can like divide it into two cases, right? You do like either U1 was 0 or U1 was 1, right? So you can just split it into two cases. And then you can substitute the things. So half times 0, half times 1. So I guess this is half. No. So U1 is half, okay. Oh, right, this term is 0.5. So this is half, this is half, this is half, this is 0. So I guess you get 1 by 4. Is that what people got? Okay, good. Right, and then you can compute PU2 equal, which is just 1 minus this thing, right? So 3 by 4. So you can compute the entropy, right? This is just the entropy of a Bernoulli 1/4 random variable. Anybody remember the answer? Okay, I will point it. Okay, thank you. Yes. So you have done this a few times now, right? Now, is this process stationary? Anyone?
I thought it was because like it's a Markov chain, so I guess it's not already stationary.
So is a Markov chain always stationary? That's the question. Not necessarily. That's why like many times in the lectures we specifically say a stationary Markov chain. In any case, in this particular example, you see we said that like stationarity is a very vast property. All statistics stay constant with time, but in particular the entropy should stay constant with time. And you saw that the entropy changed. Entropy of U1 was 1 bit, entropy of U2 was 0.81 bits. So there is no way this can be stationary. A Markov chain is stationary if you start it at a stationary distribution, which was I think question 4. So this is no, because this was actually okay, because HU2 is not equal to HU1. Is that clear? That this is not stationary, right? This was sort of a, don't worry too much about it, but just to make sure the concepts, we are all on board. Then we asked what is HU2 given U1. So let's do this quickly. U1 equal to 0, entropy U2 given U1 equal to 0, right? I think we did an example last lecture, so hopefully you all remember. So this guy, if U1 equal to 0, U2 is deterministic, right? If U1 is 0, U2 is deterministic. And this one is 1, because if U1 is 1, then U2 is Bernoulli half. So after you do the computation, you will see that these two are half obviously, so this will be half, right? If by any chance you didn't get these, look at the last lecture, we did an example, right? And just refresh your probability textbook, and I think they're just following the probability formulas. And now what we did was we changed the initial distribution, which does make it stationary. We didn't ask you to prove it's stationary. You can trust us on that. And we said, now you compute the entropy rate, right? And in the last lecture, we saw a few things. We saw that for IID, the entropy rate was just the entropy of the first one. For kth order Markov, the entropy rate was just the entropy of uk plus 1 given all the past symbols, right? So in particular for a first order Markov, this is just going to be u2 given u1, right? The entropy of u2 given the past symbol. And now we can compute it using the exact same formula. So let me try to copy paste this one. Right. So again, these stay the same, right? Now the initial probabilities change. So I think you will get 2 by 3 as the answer. Did people get 2 by 3? Yep. Sorry, are you asking a question or? Okay, good. Right. So that's it. Yeah. Just make yourself a bit comfortable, right? This is not just this class. Generally, I think this conditional probabilities you will come across in many, if you do machine learning, for example, or any sort of statistics or probability class. Right. Okay. So moving on to the material. Any questions so far on the quiz on last lecture? Okay. So the question is, how do you achieve the entropy rate? And you will realize it's very simple. So we will first start with a very simple case, the first order Markov source, right? So what is the first order Markov source again? The next symbol depends on the previous symbol. That's it. Okay. So now if you recall, the entropy rate was defined in two different ways when we looked at last time, right? There is this definition and then there is this definition. And for a first order Markov source, the second one reduces to this. Okay. So there are basically two definitions. This one, the first one says that we take the joint entropy of n symbols at a time and then we divide it by n. So this just suggests you do block coding. You just take n symbols at a time, code them together, and as you take bigger and bigger blocks, you are going to achieve the entropy rate just by definition of this thing, right? And we know how to achieve the entropy of this thing by like Huffman coding or arithmetic, any of these codes, right? The other solution is more interesting, and that's the one we'll do most of the time today, is more incremental approach where you actually try to do this conditionally. You take u1, you try to encode u2 given u1, and then you try to encode u3 given u2, and so on. So, so the first one, which is the block coding, is you can just do Huffman on blocks of length n, and then you make n bigger and bigger, and it will achieve the entropy rate. But it doesn't work very well. First of all, you can't make the block size too big, right? The complexity issues we talked about last time. And there is another issue, which hopefully you can understand, which is that when you had your usual IID symbols, right? So you had like u1, u2, u3, u4, and let's say you were like coding in blocks. You took u1 and u2 together, you took u2, u3 and u4 together. This was suboptimal because the Huffman code is only optimal for a dyadic source, right? If you have symbols whose probability is not a power of 2, you don't get the perfect code length and so on. It's not optimal, right? But here, there is another reason why it's not optimal, is that u2 and u3 are correlated. There is some correlation between u2 and u3. So if you're encoding them in blocks separately, you just lose out on the correlation between consecutive symbols. So with that in mind, do this exercise at home just to like convince yourself of these things. But let's not do it now. Anyway, this technique is not something we are going to use. This is the one we are going to use. So if everybody would pay attention, let's recap arithmetic coding. This will be crucial for the rest of this lecture. This is all you need to know about arithmetic coding in this lecture and just in generally, I think, unless you're actually going to implement it. Right. So arithmetic coding, you work with intervals, you divide the intervals into your symbols, and at every step you split the subinterval corresponding to your symbol. Right. So if you have IID model, the thing we have already studied, right, and you have 0, 1, 2, so if the first symbol is 2, you take the interval corresponding to 2, you split it into 3 parts, 0, 1, 2, which are proportional to their probabilities, right? And if the next symbol is now 0, you take the interval corresponding to 0 and you again split it into 3 parts corresponding to 0, 1, 2, whose sizes are again proportional to their probabilities. And at the end of this, very easy to see that the length of the interval that you get at the end of the encoding is simply the product of the probabilities. And the way we did the encoding in bits was that the code length was roughly logarithm of 1 by interval length, which was roughly this, log 1 by px1, px2, pxn sort of thing. Let me pause for a minute, make sure everybody understands this because we'll deal with this throughout the lecture. Right. This is like arithmetic coding in a single slide, basically.
So that expected code length, that's good like all n symbols together, right?
Yes. So that this is this thing is for the like n block, basically. Yeah, the entire block. Right. And if you recall our thumb rule, right, we said that for any symbol x, we want to pay basically log 1 by px, and you see that's exactly what arithmetic coding is paying. It's paying exactly log 1 over p for each symbol, right? Okay, so if we are happy with this, and I hope we are, we will okay, so we look at this Markov chain where every symbol can go to either itself or 1 plus that symbol, modulo 3. Look at this figure. We changed something in the previous slide. We changed the arithmetic coding, how it is done. I will wait and ask you to tell me what did we do different now. So we are encoding 2, 0, 1 is what we are encoding. Okay, let's start first. Just for encoding 2, did we do anything different when we are encoding 2 compared to the good old arithmetic coding? I can answer that one. No, we did not, right? Because we just took, we assume the initial thing is uniformly distributed and we just made 3 equal length intervals. Okay, for the next one, anybody wants to tell me, what did we do? What is different from the previous one? Yep. Yep.
So we didn't have 1, and then the next one, like the 2 in that case was gone because you cannot get to 2.
Yeah, very good. Yes. So what did we change? What we changed was, if you know that the first symbol is 2, now your probability model tells you that definitely the second symbol is either 0 or 2 with half probability. So rather than just like following blindly the old distribution, you used a different distribution here. You split the interval according to the conditional distribution, right? You split the interval according to by using the knowledge that the previous symbol is 2. And similarly for the next one, you use the knowledge that the previous symbol was 0. So therefore the next symbol can be either 0 or 1. So you just made this slight simple modification in arithmetic coding, which we will see is basically the thing to do. One thing, I think there is a question in the homework where you will see a similar thing. The one where you generate random variables. So just a hint for that. Okay, so if you are happy with that, please let me know if you are not happy with that. If you are not, just trust it's fine. Like you can follow the rest of the lecture, nothing breaks. Okay, right. So we just change the model, right? At every step, instead of splitting the interval by just like the marginal probability, we split the interval according to the conditional probability given the past, right? And in this case, because it's a first order Markov chain, you just need to look at the last symbol, but in general, you can look at the entire past, right? So whatever knowledge you have about the distribution, right, you have seen the entire past. The next time you split the intervals, you use that knowledge. And then you can do the math, which I won't spend too much time on doing, but what you will get at the end of the day is that the expected bits per symbol you get is actually equal to the conditional entropy, which is the entropy rate in this case. Maybe I'll spend a little time. So, right, you remember that the length of the interval for arithmetic coding was a product of the probabilities, right? And in this case, the product of the probabilities, you need to take the conditional probabilities at every step, because that's how we split the intervals. And so the bits for encoding is roughly log of 1 over the, everything else stays the same, right? Like the way you convert intervals to bits stays the same, just the way you split the intervals changes. Yeah, then you do the math. First term is special because there is no past for the first term, but every term after that there is a past. You use your usual formulas, and then you get roughly entropy of U2 given U1. Okay, so this is the generalized version of the thing we just saw. So this is context-based arithmetic coding. This is like the core of today's lecture. You have data, you have a model. The model may or may not be the true model for the data, right? Your data might come from a probability distribution. Maybe your model data does not come from a probability distribution. It's just you are given a sequence and you have a probability model. You have a way to say that if my past was ABCD, then my next symbol is E with probability 50%, like something like that. You have a model like that, right? A prediction model. Okay. First step, you just split your intervals according to the, basically the model has no past. So you just predict the first symbol with the probabilities. Second step, you have one previous symbol. So you predict the probabilities according to the past, the previous symbol. And next step, you basically do the past two symbols, and then you take the past 3, past 4, you just take the entire past at every step. So in this example, for example, here you see, for example, that if I know the first two symbols are 2 and 0, my model thinks that 1 is more likely to occur than 0 or 2, right? Is that clear? That this is what this model is doing. It's saying that if my previous two symbols are 2 and 0, then the next symbol is more likely to be 1 and less likely to be 0 or 2. So it's just splitting the intervals happily according to its probability prediction. The code length will be the log of the 1 over interval length. This didn't change, which is the log of the product of the probabilities. And really this is like the core. Better predictor gives you higher probabilities, right? So if you have a very good predictor, then the thing you actually observe will have very high probabilities, right? If you have a good predictor for English, then it will say that after a Q, you are most likely going to get a U. So better predictor will give you higher probabilities for the thing you actually observe. Higher probabilities lead to larger intervals in arithmetic coding because the interval length is a product of the probabilities, which gives you smaller code length. So the chain is basically better prediction gives you smaller code length. So better prediction gives you better compression. Okay, I will again wait for a second here. And like we are reaching a point where you can now forget about arithmetic coding. Just remember that better prediction gives you better compression, and that's all you need for the rest of the lecture basically. Arithmetic coding is just a tool to get you there. Any questions? Okay. Right, so this is just the same thing written in text. So as long as we can estimate the probability of the next symbol given some context. So context just means the past. Maybe you take the entire past, maybe you just look at the last symbol. Depends on the model. The model can be anything as far as we are concerned. We will look at some specific models shortly. We can use then arithmetic coding to encode the data. And the number of bits used to encode U is just log 1 over P, basically. This log rule, the thumb rule we have been seeing, right? This is what you pay. So if you're, let's just like do it more specifically, right? So good model will have P, UN given past, right? So if it's a very good model, then this will be closer to 1. It will like truly be able to predict strongly that this should be your next thing. And so then you pay basically 0 bits. So that's really nice, right? And if it's a bad model, then the probability, like a bad model would say like after a Q you are never going to get a U. So it will like be very, very bad, a bad model for English, right? And then log of 1 over like very small number is going to be large, right? So if you have a good model, good compression, bad model, bad compression, okay. This is a fun example. So Llama is a language model released by Meta. So I was just trying yesterday. If you take like a word and you try to predict the next word or a next token, and what probability distribution does it give? And I was just like looking at the top 5 guesses. So I looked at Dan, and like the top guess was thanks, I guess, in some new lingo, but okay. I don't know what than is. I see thanking, right? So we see like, but with 18% probability, it thought that THAN would be followed by a X. Okay. Then I gave it more context. I said, oh, it's actually louder than, right? And now suddenly you see that louder than words, bombs, okay. So words got 30.4%, right? So I gave it more context and you see the distribution changed. Now it thinks something different about the next word. Then I said speak louder than, right? So you might already guess where we are going. And I got words. Words is increasing now, close to 50% probability, right? So in this case, if words is the true next symbol, can somebody tell me how many bits would I pay to encode words with this model? Roughly how many bits would I pay? Yeah, I see 1, right? Why? Because log of 1 over 2, right? Half is roughly the probability here. This is 1 bit, right? So I'm at a point where given the past 3 words, I'm able to encode the next word, right? A word, if you just naively encode it, would be like a lot of bits to encode. You are just able to encode it with 1 bit at this point. And then I just basically gave it the game, like actions speak louder than, and now you see like word is like 96.5%. It can be now encoded with far fewer than 1 bit. Right. So what did we learn? We learned that the more context you give to a model, if it's a good model, it's going to be able to predict the next symbol with like more and more confidence, right? And therefore it will incur less bits when you try to compress with that model. Obviously we can do this because these models are now very good, right? If you take a silly model like from 20 years ago, just give it long, it won't do anything useful. So, right. Then I tried this, just another simple example. I tried like Stanford's data compression, right? And it suggested research, group, library, team. class was nowhere there, course class, right? Very sad. But then I said enrolling in Stanford's data compression and see how the distribution changes, course, class, program, so on, right? So the longer context you give, usually it will give you better prediction if you're using a powerful model. So that's the lesson, right? So if you know that your data comes from a kth order Markov model, then the previous k symbols are sufficient to predict the next symbol, right? If it's a Markov model, then you only need the previous symbol. You don't need this long history. But in general, for real life data, it's not a Markov model. It's not a kth order Markov model for any k. If you think like you're reading a novel, for example, right? And some character like occurs in the first chapter, and then they might not occur for the last like 5 chapters and then suddenly occur again. So then like actually having the context of the past 6 chapters is important to be able to guess the name of that character in the last chapter. So there is a limit, like computationally you can't just look at everything in the past, but our brain does that, right, in a way. Like when you're reading a novel, even if something happened in the first, I guess we flip back the pages and look if you don't remember. So, okay, we'll come back to some fun things a bit later. Again, back to the grind, right? Block diagrams. So, everything we just said can be like summarized in this sort of figure where you have a context. Context means past. You have a model. Given the model, given the context, the model predicts the probability of the next symbol, and then the arithmetic coder is able to encode it using these many bits, like for each symbol. And therefore, the total bits you use for encoding is this log loss, the sum of the log loss. Okay, anybody tell me how would the decoding work? Can the decoder, what would a decoder block diagram look like for this thing? Does the decoder need the model? Yeah, I'm seeing some nods. So basically, you remember that arithmetic decoding is very symmetric to arithmetic encoding, right? The decoder also needs to know how to split the intervals. So decoder needs the same model basically. Decoder needs to use the same model, and at step I, it will have the past, right? So decoder will sort of work step by step. At step 0, it has nothing, but it has the model, so it's able to like make those intervals. It decodes U1. Then it knows U1. It feeds U1 into the model. It gets the next step probabilities, decodes U2, and so on. So this is like iteratively able to decode. Right? Is that somewhat clear? And we'll look at some like specific models, which hopefully will make it slightly clearer. And you will have a homework question. Right. So really very symmetric, right? If we wanted to, maybe let's just let's try to draw it. So the decoder. Again, it has the past, U1 to UI minus 1. It has the model. Model gives you the probability. You do a decoding. Right, obviously there is another input, the bit array, right, like the compressed, obviously like it uses the compressed bits, and it then decodes UI, and then this UI becomes your past basically. It goes to your past. So it's like this sort of decoding where the decoder, every step it decodes one symbol, that goes into the past, then it predicts the next symbol, decodes the next symbol, then so on. Right, if you make a compressor, like make sure to write a decompressor also, right? Like some of these things, like you can get like compression of 0 bits, everything is good, but then you can't decode it. We will look at some pitfalls for these sorts of models very soon. Okay, I don't have a model. What can I do? I am just getting this data. I don't have a model. Any suggestions? How can somebody explain what they did in homework 1 when they didn't have a model, when they didn't know the probability distribution? The 5th question.
I think we just did I think in the home code we would do 50 kilobytes, and then we would just do blocks and look at the empirical distribution.
Yep. So the answer is in question 5 in homework 1. What you did was, we were doing Huffman coding back then. You would look at the empirical distribution of the input data, right? You would just make a model from the data and use that to compress the data. We used Huffman there because you hadn't done arithmetic, but you could have done arithmetic coding also. And what was the model you used in that question? Did you assume it was like a Markov model?